Welcome to an example on how to find the surface area of a function of two variables. In this example, we're asked to find the area of the surface of the paraboloid given by z equals x squared plus y squared that lies below the plane z equals 16. So our goal is to find the surface area of this blue paraboloid that lies below the plane z equals 16, which is graphed here in red. In our previous example, we found the surface area of a parametric surface given by r of u comma v. But in this example, we're trying to find the surface area of a surface given by z equals g of x comma y over the region R in the xy plane. So the surface area is equal to the double integral over the surface S integrated with respect to S, which equals the double integral over the region R, where again the region R would be the region in the xy plane of the square root of 1 plus the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared, differential A. So going back to our example, notice how if we project the paraboloid onto the xy plane, we get this circle, where because the equation of this red plane is z equals 16, if we replace z with 16 in the equation of the paraboloid, we get 16 equals x squared plus y squared, which gives us this region R on the xy plane, which is a circle centered at the origin with a radius of 4. And looking at our formula here, g of x comma y is equal to z, which equals x squared plus y squared. Now let's go ahead and find our partial derivatives. So the partial derivative of g with respect to x is equal to the derivative of x squared plus y squared with respect to x, which would be 2x. And the partial derivative of g with respect to y would be the derivative of x squared plus y squared with respect to y, which would be 2y. So the surface area, which equals a double integral over the surface S differential S, is equal to the double integral over the region R in the xy plane of the square root of 1 plus the partial with respect to x squared, which would be 2x to the second, plus the partial with respect to y squared, which would be 2y squared, differential A. Let's go ahead and simplify the exponents. So we have the double integral over the region R of the square root of 1 plus, well, this is going to be 4x squared plus 4y squared. Let's factor out the 4, so we'd have 4 times the quantity x squared plus y squared, differential A. So because the region R is a circle, let's write this using polar coordinates, where differential A is equal to r dr d theta, and x squared plus y squared equals r squared. So in polar coordinates, we have the double integral over the region R of the square root of 1 plus, this would be 4r squared, and again differential A is equal to r dr d theta. And now using the region R here, we'll determine the limits of integration. The limits of integration with respect to R would be from 0 to 4. The limits of integration for theta would be from 0 all the way around to 2 pi. Let's go ahead and evaluate this to determine the surface area on the next slide. Well, to perform u substitution, we'll let u be equal to 1 plus 4r squared. So differential u is equal to 8r differential r. So let's divide both sides by 8. So we have 1/8 differential u equals r dr, which means in terms of u, all of this would be, well, the square root of 1 plus 4r squared would be the square root of u, which would be u to the 1/2. And then r dr is equal to 1/8 du. So now if we integrate, with respect to u, we'd have 1/8 times u to the 3/2 times 2/3, which means with respect to r, we'd have 1/8 times 2/3 times the quantity 1 plus 4r squared raised to 3/2. We can simplify here. There's 1, 2, and 2, and 4 2s and 8. So here we have 1/12. So we have 1/12 times the integral from 0 to 2 pi. And now performing substitution for r, when r is 4, we'd have the quantity 1 plus 4 times 4 squared to the 3 halves, minus, when r is 0, we'd have 1 plus 4 times 0 squared right to the 3 halves d theta. Simplifying again, we have 1/12 times the integral from 0 to 2 pi. Here we're going to have 1 plus 64, that's 65 to the 3 halves, minus, here we'll have 1 to the 3 halves, which is 1. This is just a constant, so we can write this as 1/12 times the quantity 65 to the 3 halves minus 1 times the integral from 0 to 2 pi d theta, roughly 1 d theta. So the antiderivative with respect to theta here would just be theta. So we have 1/12 times 65 to the 3 halves minus 1. And we have the antiderivative, which is theta. Performing substitution, we'll just have 1/12 times the quantity 65 to the 3 halves minus 1 times, we just have 2 pi minus 0. So the 2 and the 12 simplify. So the surface area is exactly pi divided by 6 times the quantity 65 to the 3 halves minus 1, which as a decimal would be approximately 273.8666. And because it's a surface area, this would be square units, which again is the surface area of this paraboloid below the red plane, z equals 16. I hope you found this helpful.